So this video is one of the longer ones of the course, and it's concerned with introducing the periodic table. So we've already seen the periodic table in the class already, and it's this sort of like block of elements. It looks like this, and then it's divided into columns, and we'll learn that the columns are called groups, and then it's also divided into rows, and this isn't very accurately done. I'm not much of an artist, and we'll learn that the rows are referred to as periods. But it has this kind of iconic shape where it's got these two sort of like taller sections, one on the left, one on the right, and then it's got this other section that's underneath here, in the middle here, and then underneath here there is actually another section here. So it kind of looks like that. Everybody knows what it's like. And then it's divided up, and you get all of these little squares in there, and every square is where we're going to see an element. Okay, so it has a pretty iconic kind of shape and structure. And I would recommend that you find yourself you experiment and look for different versions of the periodic table labeled in different ways, and then you can bookmark those. You'll also find that there's a periodic table included in the ALEX program. Okay, so when you first start chemistry, we're going to see the periodic table everywhere, and it's for a pretty good reason, is because it's really, really helpful. So it's worth thinking about, where does the periodic table come from, and that explains in part its usefulness. So around about the early 1800s, in the early 19th century, what we realized was that we had a lot of elements that we'd discovered. In fact, we'd got to the point, there were like 50, 60 elements. And until then, chemistry students had it pretty easy. Just for every element, they just had a little note card, a little 3x5 note card, and there would be a description of the element on each of these cards. Now, when you've only got maybe 10 of these, it's pretty, you don't really need any kind of filing system. But by the time you get to, 60, things start to get really difficult to memorize all of this information. So lots of people were thinking about, how can we organize the elements to make it easier to remember the properties and characteristics of them? So the person that was probably the most successful at doing this was a guy called Dmitry Mendeleev, and it's his table that we use today. So what in the US and in some European countries and elsewhere is referred to as the periodic table, in Eastern Europe and other places they actually call it Mendeleev's table, because it's Mendeleev's system that we are using. And Mendeleev did something that was really, really simple. He took those cards that students would have with all of the properties of the elements on them, and he put those ones that were those elements that were most like one another nearest to one another, and those that were least like one another further away. So kind of like organizing people from tallest to shortest, right? You put all the tall people closest to one another, and the short people are down the other end, and you kind of you just put things nearest next to their nearest neighbor. Now when you organize people tallest to shortest, you know that if you go to the far left, you're going to find tall people, and if you go to the far right, you're going to find short people, and if you go in the middle, you're going to find somebody that's of intermediate height. So you can see the advantage of organizing a collection of things so that the objects are placed nearest to those that they are the most similar, because now you just kind of, you kind of generally know the location. Here's tall, here is short. Now, what Mendeleev found with the elements that he knew of was that he didn't get a sort of like a list of the elements going left to right. What would happen is, after a while, the properties of the elements would repeat. So he'd be going along, placing these elements nearest their most similar element, and then he'd get an element that was that was very similar to the one that was right at the beginning of the row, and then it'd go along for a bit, and then this guy, the next one, would be very similar to the one that was at the beginning of the row, and so on and so forth. So the properties would repeat, and this was referred to as the periodic. Start seeing where we get the name for the periodic table from, the periodic law that these properties would repeat. So Mendeleev was really, really, really smart. What he noticed was that every now and then you'd go along and the properties would be gradually changing, and then there would be a very big jump in the properties. And what Mendeleev realized is that that was where there was probably an element that had not yet been discovered. And so if you knew all of the properties of this element over here, so you know its boiling point, and you know its melting point, and you know its color, and you know its density, and then the same for this guy over here, then you can make a pretty good guess at what the one in the middle is going to have for those properties, right? And that's exactly what Mendeleev did. He predicted for a series of elements where those elements were missing, and also what the physical and chemical properties of those elements should be. And what this meant was scientists knew the type of thing to be looking for. So one of the examples of this is the example of Eka aluminum. So Eka aluminum was predicted by Mendeleev. Eka aluminum just means similar to aluminum. Mendeleev predicted that there should be this element that's kind of like aluminum. And anyway, and he predicted the properties for it, and then scientists went and looked for it. Now, it took them 17 years, but they found it. And when they found it, they called it gallium. And if we compare the experimental properties of gallium to those that Mendeleev predicted for Eka aluminum, you'll see that they're like really, really similar. So Mendeleev predicted that gallium would have a low melting point. It turns out that you can melt gallium just holding it in your hand. It is a solid at room temperature. We normally define room temperature as being 25 degrees Celsius. And you can melt it in your hand. So sometimes it's rumored that if you ever see people that are like magicians and they're doing like spoon bending and stuff like that, that perhaps those spoons are made out of gallium. Now, Mendeleev predicted that a gallium would have a density of 5.9 grams per centimeter cube. So it's really dense. That's about 6 times more dense than water. Sure enough, when you measure the density of gallium, it comes out to be exactly 5.9 grams per centimeter cube. Mendeleev predicted that when gallium reacts with oxygen, or he called it Eka aluminum, reacts with oxygen, it'll do so in a 2:3 ratio. That is, 2 Eka aluminum atoms will combine with 3 oxygen atoms. And sure enough, when you react gallium with oxygen, that's exactly the way that it behaves. So he nailed it, right? And he did this for more than one element. So the system works really, really well. So what do we end up with? Well, we end up with a table that looks like this. And you can see it has that structure that I mentioned at the beginning of the video, where there's these like sort of taller groups on the edges, and then you've got this lower part in the middle here, and then you've got these 2 blocks underneath. So that's pretty it. Now, that's pretty much it. Now, what you'll see in the periodic table is that each entry has a number, and it's a whole number, and that's called the atomic number. So for hydrogen, that number is 1. And then also in the entry for the periodic table is the symbol of the element. So every element in the periodic table has a unique atomic number, and you can see that none of the numbers are repeated. Now, the numbers run sort of left to right, and then we go back and we start a row over again. And some important things to remember about the periodic table is that elements that are near one another have quite similar properties, and then elements that are a long way away from one another, say francium and fluorine are going to be very different in their properties. So that's something worth keeping in mind. We can see all of the elements that are gases are kind of gathered close to one another over on the right-hand side of the periodic table. Okay, so we're going to kind of continue to look at the periodic table and break it down in all sorts of different ways. We can see some other numbers on the periodic table, and what we see are these numbers that are at the top of some of the columns. Can you see that across there? And in fact, there's numbers written in both Roman numerals and in regular, what we call Arabic numerals. We need to explain what those are. You can see that this periodic table was produced before they confirmed and approved of, if you will, the existence of the final few elements on the periodic table, but that's not important. We're really not going to be talking about these heavier or larger atoms, the ones with the larger atomic number. Every element that has atomic number greater than 83, all of these guys, is radioactive, and all of the synthetic elements are also radioactive, and they only exist for short periods of time, and we're not going to be talking about them very much. So the important thing to recognize is that rather than memorizing the properties of all of the elements on the periodic table, you just need to know how they vary left to right and top to bottom, because remember, that's how we're kind of organizing them so that ones that are most similar to each other are closest in properties to each other. So if you know the trends, you can kind of guess or you can determine what the properties are for a element that you don't have an exact list of the properties of. So we've mentioned this previously. Most elements are found in nature as individual atoms. When the atoms of these elements collide with one another, they don't stick together, with 9 exceptions. 7 of the elements, what we call the diatomic 7, are found in nature as diatomic molecules. That's your have no fear of ice cold beer 7. You can remember these by its hydrogen, and then you go over to atomic number 7 and you draw a 7. They are your diatomic elements. In addition to the diatomic 7, there is P4 and S8. Phosphorus, which sits underneath nitrogen over here, is always found as 4 phosphorus atoms connected to one another, bonded to each other, and then sulfur, that's right next door, is always found as those rings of 8 sulfur atoms bonded to each other. Remember that we need to know or have access to information regarding the physical state of an element under standard state conditions, that is at room temperature and normal atmospheric pressure. And so the important things to remember are mercury and bromine are both liquids, and then hydrogen, nitrogen, oxygen, fluorine, chlorine, helium, neon, argon, krypton, xenon, and radon are all gases at room temperature, and then everything else on the periodic table is a solid. Okay, so the elements of the periodic table can be assigned what we call a group and a period. A group is a vertical column, and a period is a horizontal row. Often the periods are not labeled. We'll talk about that in a moment, but normally the groups are. Those elements that are in groups 1A through 8A that I've shaded here, they are referred to as the representative elements. The most important thing to remember is that elements that are in the same group have really similar chemical properties. So all of these guys that are in group 1A over here, they all have very similar chemical properties. So for example, they are all soft metals that react violently with water. So that's what they all have in common. If I go over to group 8A, what these guys all have in common is they are all highly unreactive gases. So, things in the same group have very similar properties. The groups with a B in their name make up what are referred to as the transition elements. So that's these guys in the middle. Now I should point out that there are two ways of labeling the groups. There's 1 through 18, just with regular what we call Arabic numerals. And then there's these A groups and these B groups, which are numbered with Roman numerals. So the regular Arabic numerals are using what's called the IUPAC numbering system. IUPAC stands for International Union of Pure and Applied Chemists. So that's kind of like the international version. The Roman numerals are the traditional North American system, and I actually like using the Roman numerals, but I feel very comfortable flipping between the two. So when I'm talking about A groups and B groups, I'm using the North American numbering system. Now, if you look at the periodic table, you'll see that it's kind of a little weird. The numbers are not perfectly sequential. And in particular, what happens is when we get to 57, it jumps, the next one to the right is 72. And when we get to 89, the next one to the right is 104. So what happened to elements 58 through 71? Well, they're written underneath the periodic table. And similarly with elements 90 through 103, they're also written underneath the periodic table. So these guys that are written in these two rows under here are actually should really be up there. But in order to save space and so that we don't have a really long, skinny and hard to read periodic table, we pull those two rows of 14 elements, there's 14 across there, out of the periodic table, and we squash the two ends in. So these elements that sit underneath the periodic table, they're called the inner transition elements. And they're a little weird in that they don't have a group number. So if you ever get a question like, what is the group number for uranium, element number 92, the answer is it doesn't have one. That would be a trick question, okay? All right, now the periods on the periodic table refer to the horizontal rows, and they're numbered 1 through 7. Typically or often, periods are not numbered, and I recommend, so you'll have to write in the periods or just count them off. I recommend that you always count them off on the right hand side of the periodic table. There are two things to remember. Remember that these two rows at the bottom there are actually meant to go up in there, so they are in period 6 and 7. And then the other thing is, you'll see sometimes they'll break off hydrogen, and so hydrogen actually goes up there, but they're breaking it off and they're using it as a key here. So the first row of the periodic table is there, 1, 2, 3, 4, 5, 6, 7. But it would be possible to accidentally begin with 1 here. So to avoid that, and then you would be out by 1 the whole way down. You see, so to avoid making that mistake, I always suggest labeling on the right hand side, because they never break helium off to illustrate the key. Okay, so that's the kind of general layout. So at this point in time, you should be able to find an element if you were given the group number and the period number. Now, the periodic table is classified into different classes of elements. Most of the elements on the periodic table, all of those that are on the sort of the left 2/3 of the periodic table, are what we call the metals. This periodic table has the elements labeled or color-coded according to whether it's a metal, semi-metal, or non-metal. So the metals are all over here. These are all metals. Most of the elements on the periodic table are metals. On the far right of the periodic table, we've got what we call the non-metals. These are the ones that are in yellow. So they're all of these guys. Now, it should be pointed out that hydrogen is also a non-metal. So even though it's commonly written on the left of the periodic table, it is a non-metal. Now, separating the metals from the non-metals are a class of elements called semi-metals, or sometimes they're called metalloids. So that's these ones here in green. So metals on the left, non-metals on the far right, metalloids or semi-metals, separate them. Now, metals have some characteristic properties. They're pretty, they kind of have stereotypical metal properties. All metals are solids at room temperature except for mercury, and as we know, mercury is a liquid. Metals are shiny. They have what we call a metallic luster. Now, sometimes they get a little bit dull because they react with oxygen and they kind of rust or corrode. But if you take a metal and you cut it or you snap it and you get a fresh surface of the metal, it'll be shiny. Okay. Metals are good conductors of heat and electricity. So if you have a piece of metal, it'll act as a wire. You can connect it to a battery. We can, maybe you can connect it to a light bulb, right? Here's my bad drawing of a light bulb, but you can connect it to a light bulb and you can use it as a wire. Okay, so we put a battery over here, something like that. Okay. Now, if something is not a good conductor of electricity or a good conductor of heat, we describe it as being an insulator. Okay. So if you take an insulator and you hook it to a battery, it won't conduct electricity. It'll just kind of tend to get hot, and it might even melt. It just doesn't. Yeah, it just kind of doesn't work as a wire. So keep that in mind, because you will be asked to classify elements as being metals or not being metals later on. The other thing is that metals are good conductors of heat. So if you take a metal and you put it on a hot plate, and before long it's going to heat up. It's going to heat up quite a lot, and it's going to heat up quickly. So keep that in mind as well. Metals are going to be shiny. They're going to be good conductors of heat. They're going to be good conductors of electricity. So yeah, you kind of, and that's kind of an obvious one. Okay, metals have this property that you can stretch them out into thin wires and they won't break. This is also referred to as being ductile. So if something is described as being ductile, it means it can be stretched out. And this is pretty incredible. You can take gold and you can hammer gold. You can stretch gold until it's a single atom thick. You can make gold foil or gold leaf that's just 1 or 2 atoms thick. It's pretty amazing. The other thing about metals is that you can press them and you can bend them and you can make complex shapes out of them, and they won't snap. They're not brittle. Instead, what they are is malleable. So your bones are brittle, but metals are malleable. That means they can be bent and shaped into complex things without crumbling. So 2 of the groups of metals have some common names. Group 1A are given the trivial name or common name, the alkali metals. And these are famous for the fact that they react really violently with water. So some of them you might recognize, some of them you might not. Lithium, not as the pure metal, but lithium is often used to treat psychiatric disorder. Sodium is a important neurotransmitter. It's an important micronutrient, but it also is known to cause hypertension. Potassium is important in electrical signaling as well. If your potassium levels are out, then you're going to have major trouble with the rhythm of your heart. Rubidium, not really found within living organisms. It's not a major nutrient. Cesium, highly reactive metal. And then francium, it's radioactive, so we're really not going to see it. Sometimes cesium is used in imaging. It's used in nuclear medicine for imaging things. Okay, group 2A, the guys that are right next door, these are referred to as the alkaline earth metals. And some ones in here that might be familiar to you. Barium is used in medical imaging, particularly medical imaging of the gastrointestinal system. Calcium, important mineral or important component of the minerals that make up your bones. Magnesium is a micronutrient that again is it's important in all sorts of signaling processes in your body. It's also very important in plants as part of the photosynthetic cycle. So, these elements, you might be familiar with some of them. Okay. The inner transition metals are these ones that are in period 6 and 7 that appear in the 2 rows underneath the periodic table. They're often referred to as the lanthanides and the actinides. And so they're meant to go up in here, right? And there's a few in here that you may or may not have heard of. Europium and gadolinium are often used as contrast agents in magnetic resonance imaging. So if you ever had a dye injected and then been stuck into an MRI, it probably contained either europium or gadolinium. There are some other elements in period 7 that you might be familiar with. Plutonium is used in nuclear weapons. Uranium is used as a nuclear fuel both in reactors for energy and also in nuclear weapons. Thorium, you might have heard of that, is a proposed nuclear fuel. And americium is used in smoke detectors. If you look on the back of a smoke detector, you will see that it is labeled as containing americium. Everything in period 7, remember what I said, anything that has an atomic number greater than 83 is radioactive. So all of these guys in period 7 are or the inner transition metals that are in period 7 are radioactive. Okay, so we got the non-metals. They're these guys over here that are illustrated in yellow, and also hydrogen that appears on the left of the periodic table. So the non-metals have very different properties from the metals. If they are a solid, they're not shiny, they're what we call dull, and they're not malleable or ductile, they're brittle. They tend to crumble if we try to bend them or stretch them. They're not good conductors of heat or electricity. If you try and pass electricity through them, either nothing happens or they just kind of get hot and burst into flames. If you put them on a hot plate, the temperature, the heat doesn't conduct through them very well at all. We're not going to be making, pots and pans out of sulfur or oxygen or something like that because they're really bad conductors of heat. Most of the non-metals are either solids or gases, but bromine is a liquid. So we see quite a few gases in here: nitrogen, oxygen, fluorine, chlorine, and everything in group 8A is a gas. And then carbon, phosphorus, sulfur, selenium, and iodine are solids, and bromine, of course, is a liquid. So a mixture of solids and gases with bromine being a liquid. So you get a big variety in the physical state at room temperature. Remember, for the metals, that mercury was a liquid and everything else was a solid. All right. All of the elements that are in group 8A are a gas. And these are known as the noble or inert gases because except for under extraordinary conditions, they don't interact with or react with other elements on the periodic table. So they're called nobles because they're kind of like the kings and the queens. They don't mix with the lesser elements, so they maintain their purity. So all of these guys are gases: helium, neon, argon, krypton, xenon, and radon, and they're all really unreactive. Group 7A, right next door to the noble gases, are known as the halogens. And you see a mixture of solids, liquids, and gases here. So fluorine and chlorine are gases, bromine is a liquid, and then iodine and astatine are solids. Remember that the first 4 of these guys here are all diatomic, and you can see that astatine has an atomic number greater than 83, so that means that it's radioactive. All right, so the elements that are in group 7A referred to as the halogens. You do need to know that name. So we've got alkali metals in group 1A, alkaline earth metals in group 2A. In group 8A, we've got the noble or inert gases. In group 7A, we've got the halogens. Now I'm going to give the common names for two other groups that are like, you hear of them every now and then, but they're not, they're not so frequently used. Group 6A, which is the oxygen group, sometimes it's just called the oxygen group. A less common name is the chalcogens. So, yeah, that's worth knowing so that you understand what people are talking about when they mention that term. All of the elements in group 6A are solids with the exception of oxygen, which is a gas. Then in group 5A, which is the nitrogen group, these guys are called the pnictogens. And again, all of them are solids with the exception of nitrogen, which is the first member of that group. Okay, so the metalloids or semi-metals, they lie on this diagonal line separating the metals from the non-metals, and they have like properties that are in between the they have some of the properties of metals and some of the properties of non-metals. They're all solids at room temperature. A good example of a semi-metal or a metalloid would be silicon. You don't want to be confusing this with silicone. So silicon is, it is well known for its use in microelectronics, isn't it? Silicon chips. So it conducts electricity, but it's really brittle. So that's a different property from a metal. It's also dull, and it's kind of it's a yellowish color. It's not shiny at all. So it's a dull yellow. So it conducts electricity, which is a property that you would associate with a metal. But this fact that it's brittle and it's dull in color, they're properties that you would associate with a non-metal. So you kind of get the idea there. So it's a little bit of the metals properties, a little bit of the non-metals properties. It's somewhere in the middle there. Okay, so let's look at some questions here. So this question asks, in what period is argon and in what group? So let's do the group first because the group is always given. So here's argon. Atomic number is 18. Symbol AR. And the group, you have two options here, but I'm going to use the North American system, 8A. Now, what about period? Remember what I said, always want to label on the right-hand side. So it's going to be 1, 2, 3. So, period, 8A, group 3. Okay, so that's it. You could also do wrong way around, Lee. Get it right. Get it right. Group 8A, period 3. There we go. Got to be a little bit careful. Okay. In what period is lithium? So here's lithium over here. Now we want to be careful. We want to always label for periods on this side. 1, 2. There it is, right? Make sure we got it right. Yeah. So it's in period 2. And in what group? Well, we can always read the group off the periodic table. There it is. Group 1A. Now you can put 1A and you can put just plain old 1 if you want to. Any of those things will be okay. All right, now this is getting tricky. In the table below, there are descriptions of an experiment on samples of 3 different chemical elements. So we know it's an element, okay? Decide whether the element is a metal or non-metal, if you can. If there is not enough information to decide, choose can't decide. So let's think about metals. And what do we know? They're all solids except mercury. They're shiny. They're good conductors. And they are, I'm running out of space here, ductile and malleable. Now, if we think about non-metals, it's kind of the opposite there. So the non-metals, they're commonly, they could be solid liquids or gases. Bromine's a liquid. Then there's like a bunch of gases and a bunch of solids. They tend to be dull, they tend to be poor conductors, and they are brittle rather than ductile and malleable. So let's look at element number 1. Element 1 is a moderately soft yellow solid. It's not shiny, right? That's what we get from that. A 5 centimeter by 5 centimeter square of it is only 1 millimeter thick. So it's a really thin piece of this element. Is heated with a flame at one end. So what are they trying to do? They're trying to see whether it's a good conductor, right? Where the flame touches the square, the sample rapidly turns red and starts to melt, but the rest of the square remains cool to touch. So it's got a low melting point, and it just heated up really quickly into one spot rather than like conducting the heat away. So I'm going to say it's not shiny, it's dull, and it's a bad conductor. It's got to be a non-metal. Right? It's got to be a non-metal. Okay. Element 2 is a hard silvery grey. Well, that's something that I would associate with a metal, right? It's a solid. Most metals are solids at room temperature, except for mercury. And it's silvery, so it's looking like a metal. 5 centimeter by 5 centimeter square of it, only 1 millimeter thick. So a really thin layer of it, okay? Flexed slightly by hand, so you're going to bend it, okay? And all it does is it just kind of puts a bend in the middle. It doesn't crumble, so it's not brittle, it's malleable. Silvery grey, and it's malleable. It's got to be a metal, okay? Element 3 is a moderately soft silver grey solid. So silvery grey, hinting at a metal. But, there are some metalloids and non-metals that are also it's only one piece of evidence. Wires are fastened to each side of a 2 centimeter slab of it. So it looks like they're going to be testing to see if it can conduct electricity or not. And an ordinary household 9-volt battery is hooked up. So it can feed electricity through the slab to an LED. But the LED stays dark. So it can't conduct electricity, right? It can't conduct electricity, but it is silvery grey. Well, metals are definitely all good conductors of electricity, so it has to be a non-metal. Okay, let's give it another go. In the table below, blah, 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 you have to decide metal, non-metal, or can't decide. Element 1, hard grey, silvery grey solid. Okay, so potentially a metal, but it's just color, right? And people might disagree on, how you describe colors. A 10-gram cube. So it's the same on all dimensions, right? Because it's a cube, but it's a decent piece. 10 grams is, a little under half an ounce. It is set on a hot plate. So what they're doing is they're checking for thermal conductivity. And then it says after 1 minute, the temperature of the top of the cube has risen by 50 degrees Celsius. Now that's pretty good, right? Because 100 degrees Celsius is the boiling point of water, and it would take longer than 1 minute for a pot of water to come to the boil. So it's halfway to boiling, the boiling point of water in a minute. That's pretty good. It's got to be a metal. It's silvery grey, and it's a pretty decent conductor of heat. Okay, let's have a look. Element 2 is a colorless gas. Well, immediately it's not a metal, right? Because there are no metals that are gases. So it's got to be a non-metal. Okay. Element 3 is a moderately soft silvery grey solid. So it could be a metal. A 5 centimeter by 5 centimeter square of it only 1 millimeter thick. So this is like a really thin layer of it, right? It's about 2 inches on a side, this square, but it's really thin. It's only a millimeter thick. It is twisted using 2 pairs of pliers. So they're checking to see whether it's brittle or whether it's malleable. And the sheet breaks in the middle, right? And then it says the freshly broken edges are lighter colored than the surface. They're just kind of saying that, maybe it's like a little bit reactive and the outside edge is reacted with the air. But the important thing here is that it breaks, that it's brittle. Right, so that means that it's got to be a non-metal. Okay, this problem looks like we want to pull up the periodic table. So it says read each description in the first column of the table below. So we're going to read the description. If any chemical element with an atomic number of 92 or less, so anything less than there. Now the reason for that is uranium is the heaviest. It's the last naturally occurring one. That's what that's all about. So that's why they're asking about that. So we don't see things that are bigger than uranium in nature. That's why they put that in there. Okay. Let's matches the description. Check yes and enter the chemical symbol, not the name, the chemical symbol of an element that matches, otherwise check no. So it says, is there an element in period 4, group 3A? So let's label the periods 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 6 and 7, 6 and 7. There we go. Period 4, group 3A. So group 3A is here, period 4 is there. Oh, that's that gallium. There you go. And it is less than 92. It is only 31. So GA, make sure we get the case correct. A semi-metal in group 5A. All right, so where do we go down for the semi-metals? It goes down here, what we call the staircase line. So this periodic table doesn't have the semi-metals clearly like color-coded or anything like that, so you might pull up a different one. I know though, so there's group 5A semi-metal. I'm going to go with antimony, SB. There is one there. Let's go back and have a look at the semi-metals so that we can see that. There they are. You see, I picked that one there. All right. So different periodic tables work better for different scenarios. An alkali metals are group 1A with a lower atomic number than gallium. So if you remember, gallium was 31. So anything that's in group 1A with a number less than 31. So you've got a couple of options there. You could do lithium, sodium, or potassium. But then the other ones would be too big. So I'm just going to go with potassium, uppercase K. There we go. So that would be a yes. And then it says a transition element in period 2. So transition elements are these guys that are in the middle here. All right. Remember, the ones underneath are the inner transition elements. And what you can see is we don't actually get any transition elements until we are like well down beyond period 3. There are no transition elements in period 2. You see there's period 2 across there. So the answer for that one is going to be no. So in this problem, you're asked to write the name of the element family to which each of the elements in the following table belongs. And you're prompted with being told that this is going to be either a single word or a short 2 or 3 word phrase. So what this is really all about is deciding whether it belongs to the alkali metals, which is group 1A, the alkaline earth metals, which hopefully we can draw an arrow around here, is group 2A, or alternatively it could belong to the inert or noble gases, group 8A. it could belong to the halogens, group 7A. It could belong to the chalcogens, group 6A, or it could belong to the pnictogens, group 5A. So let's see what we've got. So we've got sodium, and so sodium is Na, and Na is in group 1A, so that means that it is a alkali metal. Now we've got oxygen. Oxygen is way over here in group 6A, and group 6A are the chalcogens. So they're the two families there. Okay. We're going to do the same thing again, but it says write the chemical symbol for an element belonging to each of the element families listed in the table below. So in this case, we're given the element family, and you have to give an example element, and they want a symbol, not a name. So always be on the lookout for symbol versus name. So the name is going to be it's going to be a word, and the symbol is going to be that 1 or 2 character symbol. So pnictogen is the nitrogen group, group 5A, so I'm just going to put nitrogen there. And then halogen is this group 7A here, and so I'm just going to put F for fluorine. Okay, so this is an interesting problem. It says decide which element probably has a boiling point most and least similar to the boiling point of potassium. So what we're really talking about here is, remember that the elements are organized so that they are placed nearest the things that they are most similar to. So when we're asking for something that has the boiling point most similar to potassium, we're looking for an element that is close to potassium, and preferably in the same group, because elements that are in the same group are most similar to one another. So let me see, can I see anything that is right near potassium? Well, calcium is right near potassium, and sodium is also right on top of potassium. You see that, right? Okay, so what one is it? Is it sodium or is it calcium? Because they're both touching potassium. We're going to go with sodium, and the reason being because sodium and potassium are in the same group. Okay, so now we have to decide the one that has the boiling point that is least like that for potassium. So we want, the things that are a long way from potassium. Now we know it's not going to be calcium because calcium is touching potassium. So is it going to be nitrogen way over here, or is it going to be thallium down there? So a couple of ways of looking at this is, is one further than the other? And certainly nitrogen is, more spaces away than what thallium is. And then the other way to look at this is to recognize that thallium and potassium are both solids at room temperature, whereas nitrogen is a gas. So clearly the boiling point and the melting point of nitrogen is very different from that of potassium. There's a third little bit of evidence here, and that is that nitrogen is a non-metal and potassium and thallium are both metals. So however you spin it, however you look at this, whatever reasoning you use, you're going to come up with the conclusion that nitrogen has the boiling point that is the most different from that of potassium. I mean, it's so different that nitrogen is a gas at room temperature, whereas potassium is a solid. All right, let's have a look at this one. It says decide which element probably has a density most and least similar to the density of sodium. So let's find sodium, and then the one that's going to have the density that is most similar to sodium is the one that is the closest. So xenon is way over here, so it's not going to be xenon for this, right? And then lead, there's xenon lead is in there. So that's a long way. And then we've got bismuth. And so bismuth is down here. That's also a long way. So I think it's unlikely. And then we've got potassium that is right next to sodium in the same group. So I'm going to go with potassium because it's in the same group and it's like adjacent sodium. So they're going to have very similar properties. Okay, so what one is going to be least similar to sodium? Well, you know, it's kind of obvious when you think about the physical state. Remember, we're talking about the density here. Sodium is a solid. Xenon is a gas, and remember, gases have really low densities. So lead and bismuth are both solids, so they're going to have, you know, at least densities that are like ballpark similar to sodium. But xenon's a gas, so it's like way off. Imagine, you know, you got a balloon and you fill it with like sand, which is a solid, versus a balloon that's full of gas. Obviously, they're going to have very, very different densities. So it's going to be xenon. Of course, the other thing is that these guys are metals and xenon is a non-metal. And if I think about sodium, sodium is an alkali metal. So you would expect that, you know, the fact that we're comparing a metal with a non-metal, they're going to have really big differences in their properties. Okay, so that's, like I said, one of the longer videos that we have. My alarm there is going off, which tells me it's time to wrap this up for you guys. So I hope that was helpful. And yeah, please let me know if you have any difficulties.